Okay, so let's talk about the relationship between the partial pressure of a gas in a mixture and its mole fraction. Annie, do you remember what mole fraction means?
It's the ratio of the number of moles of one component to the number of moles of everything.
Very good. Okay, so let's assume we've got a mixture of two gases, A and B. So our total number of moles is equal to the moles of A plus the moles of B. The mole fraction, that's not an X, by the way, that's an uppercase Greek letter chi, which is what we use to represent mole fraction. So the mole fraction of A is simply going to be equal to the moles of A divided by the total moles. And the mole fraction of B is simply going to be the moles of B divided by the total moles. All right? Well, let's go ahead and use the ideal gas law, which relates the moles of a gas in a mixture to the partial pressure of that gas, and simply say that the mole fraction of A is going to be equal to the partial pressure of A times, V over RT, because N is PV over RT, divided by the total moles, which is going to be the total pressure times the volume over RT. Can that be simplified, Annie?
Yes, it can. So the V's and the R's and all the T's will all cancel out to
Very good.
give you
Excellent, excellent. So what that gives us is that the mole fraction of a gas in a mixture is simply equal to the ratio of the partial pressure of that gas to the total pressure. Or another way of writing it would be to say that the partial pressure of a gas in a mixture is directly proportional to its mole fraction, the proportionality constant being the total pressure, right? So I can write this for A and B. The partial pressure of B is going to be equal to the mole fraction of B times the total pressure, right? Well, if I add together the partial pressures, PA sub plus PB, that's going to be the mole fraction of A times the total pressure plus the mole fraction of B times the total pressure. If I factor out the total pressure, I get this is equal to the mole fraction of A plus the mole fraction of B times the total pressure. Well, what is the sum of the mole fractions of the two components?
Well, the mole fractions are always going to add up to 1 when you have all the components, so that's just going to be equal to the total pressure.
Excellent. So we get back to Dalton's law of partial pressures. The partial pressure of A plus the partial pressure of B is simply equal to the total pressure. I'm going to put a box around these because these are the most important ones that show you how the partial pressure of each component relates to the total pressure. Okay? So let's look at a problem that we can do with that. I've got a mixture of 2.57 moles of argon and 6.87 moles of neon in a container, and I find that they exert a total pressure of 10.5 atmospheres, and I want to know what the partial pressure of each component is. Well, you might look at this and say, well, if I want to calculate the partial pressure of each component in the mixture, and I have the number of moles of each component in the mixture, am I going to use something like, let's say the partial pressure of argon equals the moles of argon times RT over V? Would that work?
No, because you're not given T or V.
Very good. You don't know the volume of the container, you don't know the temperature. All you know is how many moles of each component you have and the total pressure. This looks like a job for using the mole fraction.
So in this case, well, the total pressure is equal to the total pressure of argon plus the neon. So the partial pressure of argon would equal the argon, which would then be 10.5 atmospheres times 2.57 divided by 2.57 plus 6.87, and that's equal to
0.272 atmospheres?
0.272.
I'm sorry,
no,
that's not
2.
correct. 2.86, sorry. My bad, 2.86.
2.86 atmospheres. partial pressure of neon would be equal to the total pressure times the mole fraction of neon, which is equal to 10.5 atmospheres times 6.87 over 6.87 plus 2.57, which is equal to 7.64 atmospheres.
Fantastic. All right, there we go.
And
There's the partial pressure of argon right there.
yeah. And you can check your work by adding 2.86 atmospheres plus 7.64 atmospheres. And if you did it correctly, it should add up to the total pressure, and it does.
Very good. Okay, I'm going to obsessively, compulsively, if you don't mind, because I'm like that.
Uh-huh. Yeah. Because the units
This one's in
cancel
there.
out.
Yeah. Great. Okay, let's move on to the next topic, and that would be calculating the average kinetic energy of a gas particle. Gases, as you know, have kinetic energy, and you may recall from earlier in the chapter when you read about the kinetic molecular theory, one of the parts of the kinetic molecular theory says that the average kinetic energy of a gas particle depends only on the temperature. It does not depend upon its identity, it does not depend upon its mass. All it depends upon is the temperature of the mixture. And it turns out that if you go through the derivation, which is in the textbook, I'm not going to go through it now because it's not that important, it turns out that to calculate the average kinetic energy, all you have to do is multiply the temperature by R, the gas constant, and multiply that by 3/2. That will give you the kinetic energy. Well, R we know, and we've been using all chapters, 0.08206 liter atmospheres per mole Kelvin. If I take that value and multiply by a temperature in Kelvin, the Kelvins will cancel, and I'll be left with a unit of liter atmospheres per mole. Is that an energy unit, liter atmospheres?
No, it is. Well, it is, but it's not really useful for anything having to do with energy.
Very good. You could actually show that if you take liters and atmospheres, convert them to their corresponding SI units, because liters and atmospheres are not SI units, you would actually end up in joules. We're going to avoid that derivation because it's really tedious, and I'm simply going to give you the value of R in joules per mole, 0.0083145. You don't really need all 5 significant figures, but what the heck? Joules per mole Kelvin. So anytime you're using R to calculate some energy quantity, which we're actually going to be doing quite a bit later on in the year, make sure that you use this value, 0.0083145 joules per mole Kelvin. Okay? So, Annie, if I give you helium at 298 Kelvin, can you calculate its average kinetic energy?
Yeah, so the average kinetic energy would just be equal to 3/2 times 0.0083145 joules per mole Kelvin times 298 Kelvin over 1. So that would be equal to
3.72 joules.
3.72 joules per mole.
Per mole, yeah. I guess if I asked for the average kinetic energy of a single helium atom, we would want to divide that by Avogadro's number, but let's just modify the question and say the average kinetic energy of 1 mole of helium atoms. How's that look? Okay. Now, the strange thing about this, and it's a little bit counterintuitive, if I give you a mole of helium at 298 Kelvin, the average kinetic energy is 3.72 joules per mole. But what if I gave you a mole of xenon at the same temperature?
It's going to be the same because it doesn't depend on the type of atom.
Yeah, that's true. But doesn't it seem strange that they would have the same kinetic energy?
Yeah.
Even though xenon is many, many times heavier than helium?
Yeah.
So what's the difference? If they have the same kinetic energy, how do those two particles differ? Yeah.
The speed?
Yeah, exactly.
Okay.
It's what you would find is that even though these two particles have the same kinetic energy because they're at the same temperature, the helium atom would be moving at a much, much greater speed than the xenon atom because it's got a much lower molar mass. So in the next video cast, we're going to talk about what's called the root mean square velocity of a gas particle, which you will see does depend not only on the temperature but on its molar mass. Okay?